Hello everyone and welcome to chapter 4 video number 3 in the 3-phase induction machine course. In video number 1 and video number 2 we covered how to determine the machine parameters. Here in this video we are going to look for two examples on parameters determination. Example number 1. A 415 line value, and if I didn't mention line value, the default should be line value. If it's star connection, you are going to use a phase value 415 over root 3. If it's delta connection, line value equals phase value. So a 415 volt line value, 50 hertz, star connection, 3-phase, 4-pole, squirrel cage induction motor gave the following test results. We have DC test, no load test, blocked rotor test. So we need to determine motor parameters. It's a straightforward problem. So given that we have a 4-pole, the star connection, line voltage, supply frequency 50 hertz, and that one is a squirrel cage. So we are going to apply for these tests to have the approximate or first approximate equivalent circuit. So we need to determine R stator, R core, XM, R rotor, X leakage stator, and X leakage rotor. So we are going to start these tests one by one. As we know, DC test is used to determine R stator, so it's given that VDC equals 8 volt, IDC equals 6.94 ampere, and the circuit is a star connection, so we have two resistances in series. So we measured VDC and IDC, so in this case, RDC equals VDC over IDC equals 1.153 ohm. RDC equals 2R, so R, 1R equals half of this value, 0.57 ohm. But that one is not AC resistance. To have it AC resistance, you need to consider the skin effect. So R stator equals 1.11 R for 50 Hz or 60 Hz. This value is accepted. So 1.11 multiplied by 0.57. So the resistance is 0.64 ohm per phase. Moving forward to the no load test, which is used to determine RC and XM. So given that the voltage, phase voltage for the no load test is 415 volt over root 3, and the no load current is 8.56 ampere, and the no load power is 1.1 kilowatt. So the circuit, the equivalent circuit at no load is R core and XM as we see here, and this is a phasor diagram. So we are going to start from the power equation. This is the power of the two wattmeters added together. So we have in total power now P node. So P node equals 3V node I node cosine phi node. Phi node is the no load angle. Cosine phi node is the no load power factor. So from this one we can determine cosine phi node. So cosine phi node will be P node over 3V node I node, 1.1 kilowatt over 3, 415 over root 3 to convert that one to phase value, and the current is 8.56. So the cosine phi node equals 0.178, and that one will be matching what we said, that the power factor at no load is a bad power factor, so the angle is close to 90 degrees. So I core equals I node cosine phi node. That one will be 8.56 multiplied by this value. So the current I core is 1.53 ampere. And IM equals I node sine phi node. So what you are going to do, you are going to inverse the cosine, find the angle, take the sine. So that one will be 8.56 multiplied by 0.984, which equals 8.42 ampere. So you notice that core current is small with respect to the magnetizing current. And in this case, core resistance will be a high value compared to the magnetizing reactance. So R core equals V node over IC. So that one will be something like 156.6 ohm per phase. And XM equals V node over IM. So don't forget minus J for the current. So the reactance here will be J28.46. So if we consider, for example, XM is something like 30 ohm per phase and R core is something like 150 ohm per phase. So as you can see here, R core is almost 6 times XM. So here, if we take the exact ratio, it will be something like 5.5, which matches what we said before in the comments of the no load test, that the R core is 2 to 10 times XM. The last test is the blocked rotor test or locked rotor test, whatever you like. And that one is used to determine R rotor, X leakage stator, and X leakage rotor. So given the blocked voltage, blocked current, and blocked power. If You notice here the block voltage is reduced supply voltage to a value 76.9 line value. So I need to convert that one to phase value. So that one will be 76.9 over root 3. While the rated value of this machine is 415 volt, we cannot apply 415 volt to limit the current to a rated value or lower than the rated value. So we are limiting the current to 20 ampere if we apply 76.9 volt line value or 76.9 over root 3 phase value. And the power consumed in this case will be 1.152 kilowatt. And as you can see here, the equivalent circuit consists of R stator plus R rotor plus J X stator plus X rotor. And that one is short-circuiting the rotor because the slip is 1. So we are going to start from the power equation. B blocked equals 3I blocked square R equivalent. So R equivalent equals B blocked over 3I blocked square. And in this case, R equivalent, which is R stator plus R rotor, equals 0.96 ohm. So we can determine R rotor now. We are going to recall R stator from the DC test. So in this case, R rotor equals R equivalent minus R stator. Definitely considering the skin effect for the R stator. So that one is 0.64 value. And then R rotor equals 0.32 ohm per phase. Then we are going to calculate the Z or the impedance of this circuit from here. So V blocked over I blocked. So that one will be phase voltage over phase current, 76.9 over root 3 over 20. That one gives you 2.22 ohm per phase. But we know that Z equals R plus JX. So in this case, X equivalent equals root Z equivalent square minus R equivalent square, and that one gives you 2 ohm per phase. So we have a valid assumption here that X stator equals X rotor equals X equivalent over 2. So that one equals J1 ohm. So now we can put all the parameters in the equivalent circuit. We have a supply voltage 415 over root 3. That one is the rated value. And that one is supply current. It depends on the value of the S you are going to run the motor for. We have R core equals 156.6 ohm. Magnetizing reactance J28.4 ohm. 0.64 ohm per phase for the stator resistance. J1 for the leakage stator reactance, J1 for the leakage rotor reactance, and the rotor resistance is 0.32 ohm per phase. So this circuit is per phase. We are going to solve that one for whatever S we have, and this could be a starting point to find the machine performance at specific slip. Example number 2. A 220 volt 50 hertz 3-phase 4-pole delta connection. So the 220 volt is line value equals phase value for the delta connection. If the machine is a star connection, this voltage should be divided by root 3 to give you a phase value. As I mentioned before, this voltage, as I didn't mention that one is a phase voltage, that one by default is a line value. Squirrel cage induction motor gave the following test results. Determine the motor parameters at rated frequency. So the DC test reading is 10 volt, 7.5 ampere. The no-load test is 220 volt at rated voltage, rated frequency 50 hertz, and gave line current 4 ampere, and the no-load power is 250 watt. The blocked rotor test is 32 volt, frequency of the test is 15 hertz, 15 hertz, not 50 hertz, and the line current is 12 ampere, and the blocked power is 450 watt. So it's given that the voltage is 220, that one is the rated voltage, line equals phase, supply frequency is 50 hertz, that one is the rated frequency, and the machine is squirrel cage, so we need to perform the tests to determine these parameters for the first approximate equivalent circuit. Starting by the DC test to determine R stator, the machine is delta connection. The given is 10 volt, 7.5 ampere, so we need to calculate RDC. RDC equals 4 over 3 or 1.33 ohm. So we need to determine R for delta connection. R equals 3 over 2 RDC. That one equals 2 ohm. So considering the skin effect, so stator resistance is 1.11 R. So that one is 2.22 ohm per phase. The no-load test gave the following results. We have no-load voltage is 220 volt. No-load current line value is 4 ampere. So I need to convert that one to a phase value. So that one is 4 over root 3. The no-load power is 250 watt. So now we can calculate R core and XM but we need to consider the power to calculate the power factor. So P node equals 3V node I node cosine phi node. So in this case, 3 multiplied by 220 multiplied by 4 over root 3 cosine phi node. So cosine phi nodes, the no load power factor equals 0.164. So that one is roughly phi node equals 80.5 degrees, close to the 90 degrees as we know. So we can calculate I core. So in this case, I core equals I node cosine phi node. So that one in the range of 0.38 ampere. And IM is I node sine phi node. So that one in the range of 2.28 ampere. Remember that you're going to use phase values to calculate these currents. And in this case, you are going to find R core. So that one is a phase current. So that one's 220 over 0.378 gives you 582 ohm per phase for the core resistance, and XM is 220 over minus J. So don't forget the minus J here for the current. So that one gives you J 96.5 ohm per phase. Again, that one, if that one is 100 and that one is around 600, so the ratio between R core and XM is around 6. It's accepted value. Blocked rotor test. We're going to determine our rotor, X leakage stator and X leakage rotor. What's given? We have V blocked equals 32 volt. And the test is performed at 15 Hertz. In this example, we're going to follow the standards, while in example number 1, I give you the calculation at 50 Hertz. So here we are going to apply the standards or using lower frequency in the blocked rotor test in the range of 10 to 15 Hertz. So what's given here is 15 Hertz. I blocked this 12 ampere line value, so we need to convert that one to 12 over root 3 equals 6.93 ampere, and the power consumed in this circuit B blocked equals 450 watt. So we are going to start from the power, so to calculate R equivalent. So R equivalent equals B blocked over 3 I blocked square. So that one will be a phase value. In this case, R equivalent, R stator plus R rotor equals 3.125 ohm. We're going to recall the DC resistance from the DC test. So R rotor equals R equivalent minus R stator. In this case, we have 0.91 ohm per phase. What about the reactance? So to calculate the reactance, we need to calculate the impedance for this circuit. So Z blocked equals V blocked over I blocked. Let me remind you that we use the reduced voltage for the blocked rotor test to limit the current. And this equation should be phase values. So the value of the voltage is 32, phase equals line because we have delta connection, but I block should be phase value. That one will be 6.93 ampere. So in this case, the impedance equals 4.62 ohm per phase. And we know Z blocked equals R equivalent plus JX equivalent. So we can calculate here X equivalent at 15 Hertz because the test is performed at 15 Hertz. So in this case, X equivalent equals 3.4 ohm per phase, that one at 15 Hertz. So what's L? The inductance. So X equivalent over the testing frequency 2 by F, that one gives you 36.1 millihenry. So the inductance of the stator and rotor combined or equivalent equals 36.1 millihenry. If I like to have this reactance at 50 Hertz, so I need to calculate the new reactance as 50 Hertz, 2 by multiplied by 50 multiplied by 36.1 millihenry. So that one gives you J 11.3 ohm per phase. So we are going to use the assumption that X stator equals X rotor equals X equivalent over 2. So X leakage stator equals X leakage rotor, J for 5.67 ohm per phase at 50 Hertz. Now we can add all the values calculated from the tests to the first approximate equivalent circuit. We have R core equals 582 ohms and magnetizing reactance is 96.5 ohm. Stator resistance is 2.22 ohm. X leakage stator equals X leakage rotor equals 5.67 ohm. And that one at 50 Hertz. And we have rotor resistance 0.91 ohm, and all of these values are per phase. Rated voltage is 220 volt, and I stator and I rotor depends on the slip value you are going to select. So please note this circuit is at 50 Hertz. If you like to change the frequency, reactances will change. Now we are ready to simulate this machine using MATLAB Simulink. What will I watch in the next chapter? So in the next chapter, chapter number 5, we are going to simulate the machine using MATLAB, M-Code, and Simulink for the dynamic model. See you in the next chapter.